All right. So we left off on doing stuff and things. So for both of these, we are going to make alkynes, right? For the first one, you're going to get an alkyne between the two bromines. Right. And so 1, 2, 3, 4. 1, 2, 3, 4. Right. 4 carbons to start with, 4 carbons in the product. Right here, sodium amide, you're going to be able to remove the vinyl hydrogen, and that's going to make it, in this case, an internal alkyne. Right. Now, if I'm making a terminal alkyne with this, with the sodium, the NaNH2, right, you need to just remember that you need to add water afterwards to put the proton on the alkyne at the end. So you're going to make that. So far, so good? Okay, so I have taught you guys a bunch of reactions, right? But now I want to teach you guys how you can use these reactions to make stuff, right? To not just do one reaction at a time, but to do multiple reactions to make different things, right? So we're going to talk about organic synthesis. So my training um, as a chemist is as a synthetic organic chemist. So I took things that weren't very useful and hopefully turned them into things that were more useful. So, right, you build up complexity and turn useless compounds into useful compounds. Right. So you take something that is simple and you build up its complexity and you make it so it does something different or it is more useful to the world at large, right? You take a byproduct from the oil industry and you turn it into a drug to treat cancer or to treat malaria, which is what I tried to do, right? So you go from simple to more complicated, right? You go from useless thing to useful thing. So, kind of the backbone of organic synthesis is the ability to make carbanions. So, carbanions are carbons with a negative, letters would be good, negative charge. Right? So, this would be a carbanion, right? This carbon has a negative charge. It is a carbanion. or what we've been making, right? We make when we have to add water to it, right? Is this carbon here that has a negative charge? Like the terminal alkyne loses a hydrogen, it picks up a negative charge, and that is a carbanion. Okay. This is going to be our go-to carbanion to build up molecules. We're going to use these negatively charged alkynes to add carbons to molecules. So we can start out with something simple and use this to add more and more carbons to it. Okay. When we think about making carbanions, we need to think about pKa's. And we've talked about pKa's before. This is just a quick little refresher. High pKa's equal low acidity. So the bigger the number, the less acidic that compound is. Low pKa equals high acidity. Great. So for carbons, kind of the pKa's we need to think about and remember are just simple hydrogens on an alkane. That has a pKa of around 50. Hydrogens on an alkene, pKa in the neighborhood of 40-ish, 45-ish. And then the hydrogen at the end of an alkyne has a pKa of around 30. Right, so your alkyne hydrogens are way more acidic than your alkene hydrogens, which are more acidic than your alkane hydrogens. Okay. So to make these carbanions, we need to use a base. So the thing that we're going to be doing the most is we're going to be taking terminal alkynes. We're going to be treating them with base. E. That was almost an E. It took a little while. We got there. Right? And we're going to make something called an acetylide. There we go. That is what an alkyne with a negative charge is, an acetylide. There are 3 bases that we can use to do this reaction that are kind of all interchangeable, that are all kind of do the same thing, right? The first is we can take our alkyne and we can treat it with N-butyl lithium. And that's going to remove the hydrogen at the end of the alkyne, right? So it's going to remove this hydrogen and replace it with a lithium. I was right about you, Sydney. Thanks for coming back. Not you, other Sydney. You've been here the whole time. There's someone, their audio wouldn't connect and they went away and came back and went away. And so she's finally here. All right. So we have the metal on the end. And remember, when we have a metal bonded to a carbon, we can always just break that bond and say the metal is positive and whatever carbon that metal is bonded to is negative. Right? So we might draw it as carbon bonded to metal, but that's really metal plus carbon minus. N-butyl lithium, the N in N-butyl lithium is an old type of nomenclature that we've held on to forever and ever. And the N stands for normal, which just means it's a straight chain. So N-butyl lithium is just a straight chain that has a primary carbanion on the end. right? If we think about acid-base reactions that we talked about before, right? If we look at this, we have our alkyne, we have our N-butyllithium, we do a reaction, we make our acetylide, right? If we want to know if this works, wait, we compare the pKa's. pKa of an alkyne is 30, pKa of simple alkane is 50, right? The goal of every acid-base reaction is to make the least acidic molecule you can. So this reaction makes the least acidic molecule, right? You go from an alkyne that is more acidic to an alkane that is less acidic. Right? We can also use, and you already know this one, NaNH2, right? If I have a terminal alkyne and I treat it with NaNH2, I'm going to make an acetylide. I'm going to have a sodium on the end as opposed to a lithium, but for our purposes, the metals don't matter. They're just all there to balance out the carbanion, to balance out that negative charge. Right. And then the last one that you'll see used frequently, so it means LDA. Lithium diisopropylamide. So I brought up in the early class that I was like, oh yeah, this was invented at the school I went to grad school at, like back in like the 40s. And someone's like, wow, you were in grad school a long time ago. I'm like, stop it, stop it, stop it. I wasn't born like during World War II. If I was though, I aged really well, but not that old. I was like, damn, right to my heart. Right. And again, it's going to pull the hydrogen off the alkyne at the end. So why do we care? What can we do with this now that we can take the hydrogen off of an alkyne? We can use these to build up more carbons, to add more carbons. We can use acetylides to add carbons to our molecules, to increase the length of the carbon chain. So if we have an acetylide, right, we have our acetylide, we'll say it has lithium on the end. We can just add some alkyl halide. X can be chlorine, bromine, or iodide. Bromine and iodide work the best. We'll talk about why later. Right? But bromine and iodide work the best. And what will happen is the carbon that is negatively charged, which I will make red, right, will end up bonded to the carbon that had the halogen. So what happens is the acetylene replaces the halide. So you're going to end up with red carbon, blue carbon, and you end up with a bond between them. Right? So if you look at my halide, My halide has 2 carbons. What I add needs to have 2 carbons. It kind of doesn't matter what's attached, right? As long as you have that halide, you know you're going to take that negatively charged carbon and it's going to make a bond to the carbon that has the halogen, right? It's going to replace the halogen and make a new bond. Red carbon, blue carbon. Now, it's always a situation where that red carbon and that blue carbon are get bonded together. There's always going to be a line between them. You're going to connect the dots. You're going to connect the red dot to the blue dot. You're not going to smush the red dot and the blue dot together and make a purple dot, right? They're still going to be separate and they have a bond between them, right? You're not going to like put them on top of each other. So make sure you don't lose that bond and kind of smush everything together. Oh, someone in the early class had asked, "Hey, does it matter where I draw the aromatic ring?" And it doesn't. If you drew your aromatic ring like over here, that works as long as it's still blue dot. Then the aromatic ring, you're good. Right. So in all of these, you're going to find your negatively charged carbon. And your blue carbon, and you're going to put those together. So you have your red carbon right here, going to be bonded to your blue carbon. Oops. Right. And now, if you just like had a stroke like I did, you can count all your carbons and make sure you don't add any carbons or like miss any. So right, this is going to be 1, 2, 3 carbons. 1, 2, 3 carbons. Right, I can check the other side. 1, 2, 3, 4. 1, 2, 3. Red carbon is 4. I didn't lose any carbons or add any carbons. So you can always count each side to make sure that you have the right number of carbons, because you know that you're going to keep all the carbons from the alkyne and you're just going to replace the halogen. So you're not going to ever add any extra carbons. So you know that I've got 4 carbons here, 3 carbons in a line here. I'm going to have effectively a heptine at the end with 2 methyl groups hanging off. But here, the next one, I'm just going to add an iodide. No, sorry, I'm just going to add a methyl group. As such. So a lot of times these reactions will be written as a 1 arrow in 2 steps, where you'll have the alkyne, and step 1 will be your base, and then step 2 will be whatever halide or whatever alkyl halide you want to use. right? So step 1 makes the acetylide. Right? Then step 2, you add the alkyl halide to your acetylide to make your product. Right, I've got 4 carbons over here, 2 carbons here. I should end up with 6 total carbons in my line, in my compound. Right, so down here, same thing. I'm going to have step 1 makes my acetylide. Step 2, I add, right, this carbon right here is that carbon right there. Here is there.
I was asked when you know when to add water after you've added base to an alkyne.
So the adding the water after the base was when we were making, where it is right now. So how do we know to do that? So if you're making a terminal alkyne, right, with sodium amide, then you add water, and that gives you your terminal alkyne. If you're doing the same reaction, but it's an internal alkyne, you don't need to add the water. So it's only when you're going from like a vinyl halide to a terminal alkyne that you need to add the water afterwards. If you're going from a vinyl halide to an internal alkyne, you don't have to do that. And in these, right, the point of the water is you made an acetylide and you didn't want the acetylide, you wanted the terminal alkyne with a hydrogen on it. So you added water to get that H. In these, right, you're making the acetylide and you don't want to put a hydrogen back on your alkyne, or you already started with a hydrogen on it. You want to add a carbon. So you add a carbon that has a halogen on it so that your carbanion can replace that halogen and then basically end up with a carbon on the end of the alkyne. So you're basically adding a carbon to the end of the alkyne as opposed to adding a hydrogen. So we can also do this if we start with acetylene. Right here, I have an alkyne hydrogen on either side. So that means I could do the deprotonate, add alkyl halide twice. I could do it once to each side. So I could do, say, N-butyllithium and methyl iodide and add a methyl group to one side. Then I could do it again and use like LDA and ethyl bromide and add 2 carbons to the other side. Now, if you notice, I'm kind of just randomly switching bases, right? I use N-butyllithium sometimes, I use LDA sometimes, I use NaNH2 sometimes. For us, they're all interchangeable. So I'm trying to like just go through them and just like keep putting up different ones so you get used to seeing them. So that if you see one of them, you've seen enough that you know what it does, right? If you want to like commit to be like, I'm just going to use NB lithium till I die, that's cool. But don't forget that the other ones exist, so that you don't look at them and go like, oh my God, what does this do? What NaNH2? What sorcery is this, Wakefield? Right? And I'll be like, oh yeah, we're supposed to know that. So that's why I keep just cycling through them. So don't think like, oh, I want to add an ethyl, I better use LDA because he used LDA. Any of those bases will get you to the same acetylide, which will then add to the alkyl halide. So this is just me just trying to make sure that you see them enough that you know what's going on. Now, someone asked earlier, why in the first step do I not just add 2 methyl groups, right? And the part of it is acetylene's really small. And when you deprotonate one side and you make a carbon negative, it becomes really hard to take the hydrogen off the other side, right? Because that little dinky molecule doesn't want to have 2 negative charges on it, right? So the first hydrogen comes off pretty easy. The second one becomes much harder to take off because then you have 2 negative charges. So you add enough N-butyllithium in the first step to take off 1 hydrogen. Then you add your methyl iodide. And by the time the methyl iodide's added, there's no more N-butyllithium, right? So there's no N-butyllithium to react with this product. So then you can then do the reaction again, add another base, then add another alkyl halide. But you don't ever make 2 acetylides on the same acetylene. There's a lot of acetyl stuff there, right? Just because this is way too small to have 2 negative charges on it. So you can only ever take off 1 hydrogen at a time. Great, so we can go from something that only has 2 carbons, and we can build up to however many carbons we want to add. So we have a way now to increase the number of carbons we have in our chain. Doing the slides a little bit out of order, but, right? So right, so like I said, I look at organic chemistry as the ability to make stuff, right? To take things that are simple and make them more complex, take things that are useless and make them useful, right? So the example I said was like a byproduct from the oil industry. And then turning it into an anti-malarial compound, right? That's like the meat of my 20s, right? Age 24 Wakefield to 28 Wakefield was doing this with his, I would say, free time, but all his time, right? So something that is like a byproduct, right, to a possible medicine, right? Take something that is useless to something that is useful, right? But you don't just look at this molecule and go like, oh, I know exactly how to make that, right? You've got to develop a plan. Kind of like you don't look at a house and go like, I'm going to build a house and just walk over and like grab some 2x4s and start building a house. This is why like tree houses fall down because there are no plans. Just nail some boards up and hope for the best, right? You have to come up with some sort of plan, some sort of way you're going to approach it. In a house, you get a blueprint. For molecules, you do something called a retrosynthesis. Right? So retrosynthesis, you work backwards from the molecule you want to make, and you work back and you come up with less and less complex things that you could make along the way. So instead of trying to go from, 2x4 to house, right? You start at house and you think, well, what pieces do I want to put on at the end? And you work your way back to get to the 2x4 that you're going to start with, right? You go, well, I know, not an architect or a construction dude. I want to put on the doors last. Okay, cool. So you think about so I'd have the house done and I'd have the doors off, right? Then, oh, I want to put on the siding. So I'm going to take off all the siding, right? Now you work your way back piece by piece by piece, right? Until you get down to oh, take off the roof, take down the walls, and you get back to the simplest thing you could start with. The molecules are the same way. Hey, here's this big molecule. Well, I want to make this bond last. So what does that give me before? Well, it gives me that. Okay, now how can I make that? I can make it from this thing. And you work your way back till you get to your simple piece, right? What limits your retrosynthesis, right? The deconstructing of your molecule is limited by the possible / known reactions, right? So you can use any reaction that's possible when you're making your molecule, but you can't say I'm going to make this bond, but then there's no way known to make that bond, right? You need to use the tools that you have, right? You need to use the reactions that you have. You guys are limited more on the reactions that you know. All the organic chemistry reactions you know are basically 15 or 18 reactions. That's all you know. That is all the tools you have in your tool belt or your toolbox, wherever you keep your tools. That is all the tools you have, right? Are those 15 reactions. So when you work backwards from something, you have to think oh, how do I know how to make this thing? What are the tools I know that I need to make this thing? What do I need to have to use those tools beforehand, right? So an example is, let's say we have an alkyne and we want to make, in some number of steps, we want to make, we'll make a different ketone. Sorry. We want to make this ketone, right? So what you have to do is you have to think okay, I want to make that ketone. Where do ketones come from? How do I know how to make a ketone? What do I need as a starting material to make a ketone? Where do ketones come from? Ketones come from aldehyde. They're from alkynes, right? You have an alkyne, you add water, sulfuric acid, that turns the alkyne into a ketone. So to make a ketone, you would have to have an alkyne first, right? This molecule has 6 carbons. This molecule has 2 carbons. So you've got to add carbons to your acetylene. So we just went over how to do that, right? If I had 6 carbons, the thing I would have before would have 4 carbons, right? It would have the 2, you'd be adding these 2 carbons. And then this, I know how to get from here back to there. So in a retrosynthesis, you're kind of laying out what key compounds you need to make along the way to get to your compound. Now going forward, right, you're going to make each of these key compounds to make your product. So I have my alkyne. How do I go from my alkyne? Keep it the same. How do I go from that acetylene to, this is what, 1-butene? How would I do that? Two steps. One of them definitively is a base, but I need more than just base, right? Give me a specific base. There are three. Trace bases. NaNH2, right? Now I need to add 2 carbons to this acetylide that I just made. So, right, that's 2 carbons, and then pick your favorite non-fluorine halide, bromine, because it starts with the same first 2 letters as my name. There we go. That's why it's my favorite. Antimony, right? That's AN. There you go. Done. Lithium. See, look at this. See? We can do this all day. See, SY is hard. Right? I was like, silicon. No, that's not right. That's not right. Just SI. Right? Now I've got, from here, I need to make, right? I said I need to go from 4 carbons to 6 carbons, right? So now I need to do effectively the same thing again. We're going to pretend like I ran out of NaNH2. So I'll use N-butyllithium this time. And then we'll again add our ethyl bromide. Now, how do I get from an alkyne to a ketone? No, that's if it's a terminal alkyne. If it's a terminal alkyne, it's something, something, and hydrogen sulfate. If it's an internal alkyne, it's those 2 somethings. It's water. If it was terminal, it'd be water, hydrogen sulfate, and something else. When it's internal, it's just water and the something else. We're getting closer, though. It's here. No. Again, that's for the terminal. For the terminal alkynes, you're 100% right, but for internal alkynes, we don't need that. Not H2O2. SO4. Sulfuric acid, water sulfuric acid, the same thing that we use to hydrate an alkene, we use to hydrate an alkyne and turn it into a ketone. And for everyone who was saying, for if it was a terminal alkyne, right, then you need water, mercury sulfate, and H2SO4. This will work for an internal alkyne, but if you don't have to use mercury, don't. Right? Dying's bad. Never done it, but I assume it's bad. All right? Kind of like heroin. Never done heroin, assume it's bad. I went to grad school with a guy who was like, I've done every drug. What heroin? It's because I never met anyone who was like, damn, I'm glad I started doing heroin. And I was like, that's a good rule of thumb. Like maybe you've met someone that's like, I love meth, but no one's been like, I love heroin. I'm like, oh, cool, thanks. Thanks for that clarity. I will tell future generations this is how they should live their life. If you ever met anyone who's like, I'm really glad I did this, then don't do it. All right. Now, that's not to say if you do meet the weirdo who's like, I love heroin, best decision of my life, you'd still be like, you live in a box. I don't know if you're like the best person to be telling me stuff right now. You're high on heroin. That's why you're saying this. You're thinking shit. Okay. Okay. Now, what I have found through experience was No, I did the thing. Crap. That's right. I have to cut it out of the last 10 minutes. Okay. Is if I were to just give you this and say, hey, make that. I did something like this on the very first exam I ever gave. And I graded roughly, carry the two, like 40 out of 45 blank pages. And I was like, oh, that was good for me because I like didn't have to actually grade anything. I just turned the page and went wrong. Next page, wrong. Right? But that didn't do anything for anyone else. So what I do instead is I will give you a I'll give you like handholds along the way. And I'll be like, okay, hey, you have an alkyne? Right? Get from that alkyne to this other alkyne. So I'm kind of giving you a sense of how many steps there are, right? And I'm kind of doing part of the retrosynthesis for you, right? If you're seeing some of the, at least one of the structures that you need to get to your compound, right? What this doesn't eliminate, it doesn't eliminate that ability to look at a molecule and go, huh, how do I know how to make this? What things needed to be there before this molecule for me to get to this molecule? So like if we look at this compound here, right? You're like, well, I know I have to, I'm starting with something that has 2 carbons. I'm getting something that has 6. So I've got to add carbons to it, right? So B could be that, right? So how do I turn acetylene into B, right? Again, it's like LDA, and then I've got to add 1, 2, 3 carbons, add 3 carbons, right? Have 3 carbons with a halide on the end. Now I've got to add 1 carbon. Right, then I could use N-butyllithium and methyl iodide, and I could add my 1 carbon. So now if we look at this, how do you know how to make a vicinal dibromide? I'm hourly, I'll wait. How do you know how to go from something to 2 bromines on adjacent carbons? Test one. Sorry, there's something in my throat. Sorry, it's the Rona. Yeah, so you'd add Br2. Now, you said you had 1 equivalent, and that's when you have an alkyne, and that would give you a double bond between the 2 bromines. Here I don't have a double bond, right? That means I started with an alkene, right? So E, because of this product, right? And I only know one way to make bromine single bonded carbon, single bonded to carbon, single bonded to bromine, is I had to have a double bond and I had to treat it with Br2, right? So because you know that's the only way you know how to make this, that tells you what F is, that it has to be Br2, and then you have to know what F has to react with, and that is a double bond. Now, I'm going to show you in a second, or Friday, maybe in a second though, How I know it's a cis double bond. But trust me, it's a cis double bond. How do I turn an alkyne into a cis double bond? As someone pointed out before class, the final in this class is cumulative. But basically, every single test you take is cumulative. So you're not allowed to forget anything ever. In this, we went over like Monday or Friday. Like it was super recent. So how do you get from an alkyne to a cis double bond? Lindlar's catalyst. So H2 in Lindlar's catalyst is going to get you to your, wait a minute, your cis double bond. Hopefully the AirPods charge quick enough. We're at 1%. These poor little guys have been abused. They're just like, they listen to music a little bit. Now they're just like my lifeline. They're like, why, dude? Can we go back to listening to podcasts and not having to do work? I'm like, no, I can't. You can't. All right. So, real quick. If I have a trans double bond and I use Br2, right? I get a bromine on one side of the double bond, on one side, bromine on the other. They're on opposite sides. Somehow the right one charged to 81% and the left one charged to like 2%. Good job, guys. So if I have a cis double bond, right, the mechanism says the two bromides need to be on opposite sides, and they are, right? But we normally don't draw our molecules like this, right? We don't draw them where they're basically the like eclipse conformation, right? We draw them so they're like effectively anti-staggered, the carbon chain. When I rotate around this bond, this bromine stays up, and to rotate around that bond, the bromine that was back ends up on the same side, right? So if you see your bromines or your OH and your halogen from a halohydrogen synthesis on opposite sides, right? You expect them, then you know that that was a trans double bond. If they're both wedged or both dashed, that's because you had a cis double bond and you rotated around the single bond after the reaction. And with that, that'll be a class.